Right. Thanks for coming. It's the last day of the workshop, and we're happy to have Michael Celentano talking about the estimation error of first-order methods.
Thank you. So today I'm going to tell you about some joint work with my advisor, well, I just arrived at Berkeley, but I finished my PhD at Stanford a few weeks ago with Andrea Montanari. Yuchen was another PhD student there. The topic I'm going to talk about is the same topic that Andrea discussed at the workshop, but I'm going to tell you a few different things about it. In particular, I'm going to try to present to you an alternative technique, which is actually probably a bit more complicated than the one that he presented, but I think is interesting nonetheless. Okay, so the type of model that I'm looking at is a high-dimensional regression model. So we're going to observe, we're going to receive n samples. Each comes with an outcome y and p covariates in this vector x. And the outcome is generated according to some kernel p that depends upon the covariates of the features linearly through this parameter theta, which is the object of estimation. Okay. And we're also going to observe this side information V0. And V0 may be informative about the unknown parameter theta. In particular, the sort of coordinates of theta and V are going to be generated jointly according to some known prior distribution, which I'll call mu theta V. Okay, we're going to be interested in the proportional asymptotic. So N and P are going to diverge, and their limiting ratio is okay, so there's several algorithms or iterative algorithms that you could use for estimating theta. A class of algorithms that has come up several times in this workshop is approximate message passing, which takes this form. So we're going to keep track of the sequence of iterates B in n dimensions and iterates A in t dimensions. And the A and P algorithm is going to be fixed by a choice of F and G for each time iterate t. And then the A and P algorithm is as written here, where the alphas and the betas are chosen in a particular way that is determined by the model and the choice of functions f and g. Okay, and provided that alpha and beta are chosen in that way, we get to call this an A and P algorithm. And after t iterations, we will estimate the unknown parameter theta by applying some function g to our iterates and the side information. Okay, so that's A and P. Several people have written. Okay, so this is a figure that I took from a paper by Barbier, Krzakala, Macri, Milan, and Deborova. This is just a concrete example of a high-dimensional regression model. So this is the sparse phase retrieval model in which we observe the absolute value of this linear measurement of theta. And okay, the sparsity parameter will be denoted by rho, which is the ratio or the fraction of coordinates which are of theta which are active. And okay, not all of the lines in this figure are going to be important for the talk, but this black line is the information theoretic threshold. So if we have sort of fewer measurements than active coordinates of theta, then recovery of theta is impossible. And this solid red line is an algorithmic threshold. So this is the threshold for a particular A and P algorithm called Bayes A and P. It's sort of conjectured to be what's achievable by any polynomial time algorithm, but in this paper, it's just presented as the recovery threshold for this algorithm Bayes A and P. And we need substantially more measurements than is information theoretically required to recover the unknown parameter. So this is perhaps a good example to keep in mind. What we're going to do is we're going to sort of establish that this threshold is a threshold for a much larger class of algorithms. So here's another algorithm, it's gradient descent. We're going to define some objective, which is has a loss term and a penalty. I've chosen them separately. And gradient descent, which everyone knows, takes steps down this objective. And I've expanded the form of the gradient here. And the important thing is that it sort of looks like A and P in a certain sense. The sense being that it involves two types of operations. First, in green, multiplication by our design matrix or its transpose, and in red, application of some function coordinate-wise to the iterates or some function of the iterates. Okay. So the observation is that many algorithms involve only these two operations, matrix multiplication and coordinate-wise nonlinearities, which motivates our definition of the class of general first-order methods, the definition is just that it's an iteration which only uses these two operations. So we get to choose 4 functions which map from t+1 variables to the real line. And the first order method keeps track of a sequence of iterates in n dimensions, now called u, sequence of iterates in p dimensions, now called v. And these functions are applied row-wise. So we have t+1 vectors. Each of these is n-dimensional, and we apply f sort of to each row of the matrix that has those as vectors as columns. And this is the first order, the general first order method. It's not A and P because this sort of second term is not necessarily chosen in this special way, which allows us to call the algorithm an A and P algorithm. Okay, so, and this, will include, for example, the gradient descent iteration I showed on the previous slide. Okay, and after t iterations, we estimate theta using some other function applied to the sequence of iterates up to that point. Okay, and our result is going to be a lower bound on the estimation error of any general first order method in the sort of fixed t and going to infinity asymptotics, which corresponds to time that's linear in the size of your data. So what is the lower bound? Well, the lower bound is going to be of the following form. It says that the sort of limiting estimation error at fixed t is the risk in a particular scalar model of Bayesian estimation. And the particular scalar model is going to be the following. We're going to receive a single noisy Gaussian observation of a scalar random variable theta. And we're also going to observe some scalar random variable v. Theta and v are going to be generated jointly from the same prior that generated the coordinates of our high dimensional regression model. Here's the lower bound stated in a bit more completeness under the fixed t and going to infinity asymptotics. The asymptotic estimation error is lower bounded by this Bayes risk in the scalar model, where this tau t, the noise variance in the scalar model, is determined by the state evolution of this Bayes AMP algorithm. Now what have we established? That the sort of optimal first order method is, in fact, this Bayes AMP algorithm. Okay, now of course the risk of Bayes AMP is bigger than the Bayes risk, but what's interesting is that sometimes it's strictly bigger than the Bayes risk in these high dimensional regression models. We know from these authors what the Bayes risk is and what the risk of Bayes AMP is, and so we can identify exactly what these gaps are. Okay, so those are the results. And now for the rest of the time, I'm going to give you a taste of the technique that we use in our paper. Okay, so the way that we're going to prove this lower bound is we're going to compare the regression model to a separate statistical model. And the separate statistical model is going to live on a completely different space, but it's going to be very similar or similar in several ways to the high dimensional regression model. Okay, and I'm going to walk through several aspects of both of these models in the remainder of the talk. So first, I'm going to give you the statistical model. And I'm going to give you a class of algorithms in each model. So I've already told you about the class of algorithms for the high dimensional regression models. They're the first order methods. And on the computation tree models, I'm going to give you a algorithms, which are message passing algorithms. I'm going to describe to you the asymptotic error of these algorithms. Okay, so the asymptotic error of the general first order method is going to be given by some state evolution, and likewise the asymptotic error of the message passing algorithm will be given by some state evolution. Okay, and in both models we'll also have a description of the Bayes risk. These sort of are two storylines. They run sort of in parallel. Okay, so two stories. And of course, these two models are going to be related. So the models are going to be in bijection with each other. So each high-dimensional regression model is going to be in bijection with some computation tree model. And each first-order method in the high-dimensional regression model is going to map naturally to a particular message passing algorithm on the corresponding computation tree model. And the important thing is going to be that under this mapping, the asymptotic error achieved by the first order method is going to be the same asymptotic error achieved by the message passing algorithm. Now, this asymptotic error is greater than the Bayes risk in the regression model, and likewise on the computation tree. But this sort of correspondence between the two worlds doesn't actually extend to the Bayes risk. So the Bayes risk might be different in the two worlds. And so what I get is, okay, I get this inequality trivially, but now I can bound this sort of algorithmic error in the regression model using this sort of string of equalities and inequalities. I get that the algorithmic lower bound, or the lower bound on the first order methods in the regression model, is greater than the Bayes error on the computation tree. And the Bayes error on the computation tree might actually be larger than the Bayes error in the regression model. And so I've established a gap. So this is okay. I mean, actually, I could just end my talk here. I think this is the main idea. Okay, so now I'm just going to go through this in a bit more detail. Okay, so high dimensional regression. So I've already told you this. This is my model, step one. Okay, so this is just a repetition of an earlier slide. I should tell you a little bit about more than I've already told you about the class of algorithms in the regression model. So the main observation, which is not actually that difficult of an observation to make, is that after a sort of change of variables, any first order method can be reduced to an A&P algorithm. Okay, so if you give me a first order method, which is defined by these functions and some G star, then, okay, there's some A&P algorithm, meaning there's some choice of F and G, so that the iterates of the A&P algorithm, A and B, are related to the iterates of the first order methods through some simple change of variables. Okay, so that I can sort of design an A&P algorithm with F, G, and G star, so that this theta hat is exactly the same as the theta hat that is given to me by the first order method. And there's no asymptotics there. That's just an exact equality. Okay. Okay, so I'm only going to consider A&P algorithms on the regression model without loss of generality. Okay, and this is state evolution, which I think several of you are familiar with. The state evolution tells us that the iterates of the A&P algorithm look like Gaussian observations of the unknown parameter theta. Applied to studying the L2 estimation error, that statement tells us the following, that the A&P error, which I've written here, and I've expanded here, looks like this object asymptotically. So now I replace the sort of A&P iterates with some Gaussian observation of an unknown scalar quantity. This is the sort of asymptotic error of some estimator that received Gaussian observations in the scalar model. And in order for me to sort of fully specify to you what this statement means, I need to tell you, well, two things. I need to tell you what these coefficients alpha are, and I need to tell you what the covariance of this Gaussian noise is. And that is what state evolution is. So I won't write it, but this is fully explicit. Okay, so great. So summarizes what I just said. We get our high dimensional regression model and some specification of the functions that are used by A&P. There's some function called state evolution that maps that to some scalar model that gives us, for example, the limiting L2 estimation error. Okay, and the Bayes risk is something that we know. It was established for linear models by Reeves and Pfister, and then for generalized linear models, this larger class of high-dimensional regression models by Barbier and et al. I've given you what I've promised, which is the 4 steps of my story about the high-dimensional regression model. Now I'm going to give you the same 4 steps for the computation tree. Okay, so I haven't even told you what the computation tree model is yet. So the computation tree model lives on an infinite tree. There's 2 types of nodes. There's variable nodes and there's factor nodes. This tree sort of gives us the sort of structure of observations in some statistical model. So to each variable node, I don't receive, but there's some unknown scalar parameter, which I'll call theta v, some side information v, which I do observe. Factor node, I receive an observation that tells me something about the scalar parameters or unknown variables associated with the variable nodes that border the factor node. Okay, so in particular, I receive some noisy observation of this linear combination of the variable nodes in my boundary. Okay, and the sort of objects that enter into this model are the same ones that enter in the high-dimensional regression model, so that this one-to-one correspondence should be pretty clear. Right, this prior mu is going to agree with the one in the high-dimensional regression model, and this kernel P is going to agree with the one in the high-dimensional regression model. And okay, the ratio of the sort of, there's going to be each factor node is going to have n neighbors, and each variable node is going to have p neighbors. Okay, so all right, that was the model. Now we're on to step 2, which is the message passing algorithms, or the algorithms, which in this case will be message passing algorithms. And the message passing algorithms I'm going to consider at each iteration pass a scalar quantity from variable to factor node and from factor to variable node. And the scalar quantity that is passed is as follows. So it's specified by some choice of functions f and g. The message from the variable to the factor node is some linear combination of these sort of aggregation of messages that were incoming from the factor nodes to V. And likewise for the factor to variable node pass. Okay, that's the message passing algorithm. If I want to get an estimate of the unknown parameter at a single variable after T iterations, I apply, well, first I construct this, okay, maybe these should have been written in different order. So first I construct this AVT, which is some aggregation of the messages incoming to that variable node at iteration T. And then I apply my sort of star, which aggregates the messages from each iteration of the algorithm. Yes. Yes. Sorry. So this is the side information. So yep, I guess there's a typo. So yes, so I guess I should have put it as 0 here or not a 0. Yeah. This is the side information.
Side information or any side?
Any side information, yeah.
Okay.
Okay, on to step 3, which is the state evolution. It's the same sort of state evolution that we have for AMP. So we get that the iterates of the message passing algorithm look like Gaussian observations of the unknown parameters. So in particular, the risk at iteration T is, okay, here I've rewritten it, and asymptotically, it looks like the same risk you would get in this scalar model, where now the sort of scalar model I compare to is exactly the same as the one I compared to in the high-dimensional regression model. So it's coefficients alpha, and these coefficients and this covariance T is the same as I would get by running the AMP algorithm with the same choice of functions f and g. Okay, so the Bayes risk on the computation tree well, I'm going to actually compute sort of a local Bayes risk. So the thing to observe is that message passing algorithms are local. Okay, so at each step, they sort of aggregate information just from their neighborhood. And after T steps, the only information that I have access to at node V is the information that occurs out to a radius in the tree of size 2T. The computation, so each variable node has P neighbors and each factor node has N. The sequence of these models, where N and the proportional asymptotics. Yeah. Okay, so there's sort of a Bayes risk, which is now not restricting myself to message passing algorithms. I want to come up with the best statistical estimator under the constraint that I only observe information that lives within a radius 2T neighborhood of my variable node. Okay, so I can compute this posterior exactly using belief propagation, which is sort of a message passing algorithm. It's not of the form I showed you because it tracks more than just scalar quantities, but it's described asymptotically in the N over P going to delta proportional asymptotics by a state evolution. So it's summarized by a few scalar quantities, the same scalar quantities that summarize A and P. And its state evolution is the same as the state evolution that Bayes A and P has. Okay, so in particular, the sort of, okay, what you get is that actually that the Bayes risk is equal to the risk of Bayes A and P, or said equivalently, Bayes A and P is a sort of simpler way of running an algorithm that achieves the Bayes risk on the computation tree. Great. So the local Bayes risk is the risk of Bayes A and P. And we already, something that I already showed you in the plot for phase retrieval is that sometimes the risk of Bayes A and P is worse than the Bayes risk in regression models. So I've already shown you sort of that there's a difference between the Bayes risk on the computation tree and on the high dimensional regression model. Okay, so that's the argument. So I've given you what I've promised, which is this storyline in the two models. Here's another outline of it if you'd like. So in the high dimension, on the top, I have sort of high dimensional regression models. On the bottom, I have the computation tree. First, I reduced first order methods to A and P algorithms. I showed that these have a state evolution. I showed message passing algorithms on the computation tree have a state evolution. These are the same state evolution. And then I was able to make compute the Bayes risk in both models. Well, that's the goal. So do I have time? Maybe I'll stop here. So yeah, so I'll just quickly say a bit more about the sparse phase retrieval model. So here's a theorem that you can get from our results that, if you have some side information that is Gaussian, then sort of if you're below the spectral threshold, which is the threshold above which spectral methods begin to achieve non-trivial correlation with the unknown parameter, then you have sort of this minimax bound. So that's sort of the quality that the sort of estimation error that any first order method is able to achieve is not, substantially larger than what you could have achieved just by looking at the side information. Hence the side information too much. Okay, before I finish, I should just give a plug for we're going hiking today at 2. I'll be leading that hike. I'm actually new to Berkeley, so I don't actually know if this view occurs on our hike, but hopefully something equally attractive. So I hope to see you there. We'll be meeting outside Simon's at 2. Thanks.
Yeah, I think we have time for a question.
So what does your result say anything about initialization? Like suppose you were to run initialize, run over and over again, iterations, things like that.
Does the result say anything about initialization? So, okay, what do you, I mean,
It makes sense, I'm not sure.
so I think, so often what you want to do is you want to, like in the phase retrieval model, you want to use a spectral initialization, and that is not, this sort of side information is really just a crude way of trying to capture what maybe a spectral initialization would achieve. But, yes, I think a more powerful and interesting result would be to incorporate the spectral initialization into whatever lower bound we produce. But that's sort of, spectral initialization is not something that is a first order method. So it's not something techniques. The only sort of initialization that you can have is one that is sort of uncorrelated with this. You can't use this data matrix X to construct your initialization. You have to use noise or something that's independent of that. I don't know if that answers your question.
Okay, that's perfect. Yeah, but you can use some information, which, as you say, arises in the side information.
Yeah. The side information is not, correlated with X.
How strenuous is the hike going to be?
What?
How strenuous is the hike going to be?
I think it's going to be
Can we get that?
some.
No, the one at that.
Oh,
Maybe
oh.
let's transition.
Okay. The question was, how strenuous is the hike going to be? That's going to be a function of how ambitious the attendees are going to be. I think. It's going to be. There's no. I think however hard people want to. We're going to go up to the fire trails behind campus. So.